Good evening and welcome to another session with me, Varun, on Tech Tablet. In this video, we will be looking at the Unit 5, which will be broken down into two parts, that is 5.1 and 5.2. And the name of the unit is Advanced Topics in Data Science with R. Now, what do we mean by advanced topics? What might we have? So here we have four topics that would be covered like usual. The first topic would be concept of time series. The second topic that we would be discussing would be time series objects in R, which is majorly discussing, what are the different types in which time series is consumed. The third one is, majorly for understanding what is decomposition of time series and what is plotting. How do we plot? And finally, the last topic that we have is stationarity and differencing, right? Now, to understand these, we'll have to go through a lot of topics like Arima, Sarima, Garima, and all, but we'll try to keep the, the syllabus or the technical discussion as close to the syllabus as possible. Having said this, now let us understand what do we mean by time series analysis. We all know the meaning of the word analysis, right? Now, what do we mean by analyze? Now, let us say you have a problem statement and you're trying to understand it deeper. And when I say you're trying to understand it deeper, it is through numbers, it is through graphs, and through pictorial representation. So, what happens in analysis? You are basically having a deep understanding, right, of the problem or of how to handle the problem. Deep understanding is, something that we acquire through data. Okay. Now, data science or analysis is nothing without data. So having a data is mandatory. Now let us understand what are the key components involved to be able to do this. The first one is trend. We all know the meaning of the word trend. Trend is a long-term upward, like, the graph in the graph. Okay, so let me just, draw it here. So now here I would be coming up with a graph. This is x-axis, this is y-axis. Now, as you can see, in 91, this was my sale. In 2021, this is my sale. So this here is very clearly an upward trend, right? Then you have downward trend as well. Now imagine something like this. Okay, so how we can see in cases like these, the business is falling. In 1991, my business thrived, but in 2021, it has come to an end. So it's either long-term upward or downward movement of the data. Then we have seasonality. What do we mean by seasonality? Seasonality is repeating pattern or repeating behavior of a data. Now, what do you mean by repeating behavior of data? Now, let us assume you are a clothing store, a winter clothing store. Okay, just for the sake of example. Now, how would you notice that your clothes get sold? Usually in summers, people do not buy that, but in winters, your sale might go through a lot of, motion. So this is called seasonality. That means based on the season, you would be noticing different changes in your business behavior. Then you have noise. Okay, noise is mostly the unwanted data. Okay, whenever you have a lot of noise, it means that you have unpredictable fluctuation that remain after removing trend and seasonality. So now let us say during the pandemic, that is Corona, we saw how the sale of masks suddenly rose. It was not like that till Corona happened that, we needed masks mandatorily. So this is how we can understand time series analysis using trend, seasonality, noise, and other features. Right? Now going forward. Now, what are the different components involved in time series now? Like, just to have a basic level. Trend, as you have seen, it represents the long-term progression, the growth or decline. Okay, a lot of people assume that a trend is only growth, but even if it is decline, it is still called a trend. Then you have seasonality. cyclic patterns that repeat over a fixed period of time. These are not indefinite or these are not infinity, okay? They have a usual definition window of 6 months or 1 year or 2 years, and we would be measuring the seasonality within these 1 or 2 years. When we have noise, as you can see, it is the residual variation unexplained by trend or seasonality. Noise in some terms is also called error, but in time series analysis, I don't think it can be considered lightly. All right. Now going forward, there are a lot of real-time use cases that we can talk about when we look into time series analysis. Here we have prediction of ice cream sales. So what we are doing is, let us understand the problem statement. So you have a small ice cream shop that records its daily sales at every month for 3 years. Okay. So you record your daily sales every month for 3 years. So you have the information of last 3 years of data. Now, is it possible for anyone to predict how much sale you will have in the next month or in the next summer? Oh, yes, you can. And that is exactly what time series does. So when you're using time series, you would be able to understand the behavior of the ice cream shop. When would people buy? At what season would you see a high? At what season you would see, peak and lows? So all these can be understood. So that is trend. Then you have seasonality. Seasonality talks about in which month your sales would go to highest. Like your sales would shoot up in summer because it's an ice cream, sale. So in summer, people eat a lot of ice creams. In winter, it reduces. And this is a repeating cycle because every year, winter, people reduce eating ice creams. Okay. And then you have noise. Some random days have unusually high data, even because of some bad weather or anything like that. And here we have a small code written. Okay. Now, what are we doing here? Here, I am, taking TS. TS stands for time series. Okay. So the function in R to be able to execute time series is TS. So here I have a data which is ice cream sales. Then I have the start date and the frequency. Why is the frequency set at 12? Because every year you have 12 months within an year. Okay. So you are planning to generate a graph for them and check if the seasonality is varying on an yearly basis. In the next step, you would be plotting them. Okay. After you plot them, you would finally decompose the information. Now, what happens when you decompose? Okay. This is not a biology related word. Please mind you. Decompose basically is used when you want to remove, extra noise, etc., everything. And then you're trying to see the trend or the seasonality within the information. That is where you use decompose. So what did the model predict? Now that you have finally come out with something good, what did the model predict? Let us understand the process first and then let us see how does the model predict. Okay. So first step is to visualize the 3 years of monthly sale. In the second step, you would be splitting the data into trend, seasonality, and noise. Now, in order to do this, you have a function in R which is called decompose. Okay. Now, once you have decomposed the information, you would go into step 3, which is to fit the model. Now, how do we fit the model? To fit the model, we have a function called auto.arima. Now, we'll just look at this and what it does. So, we use auto.arima to automatically find the best forecasting model. Okay. Now, let us understand what is ARIMA. I'm just trying to mention the meaning of ARIMA here. So let me write it down. ARIMA. So here AR stands for auto-regressive. I stands for integrated. And then MA stands for moving average. So ARIMA here in this case, it means auto-regressive integrated moving average, right? So auto-regressive is understood, okay? Then you have integrated. So this basically tries to differentiate your data X number of times based on the data set, okay? And then finally, the moving average of the data points is calculated. And once all this step is done, here you can see the model predicted a 15% sales increase in the next June. Okay. So just a quick question for all of you. Do you think this information here can be used to, predict data or not? Think about it and let me know. So when we are using time series analysis, we have certain functions available. Of those, the first one that we have available is TS. The second one that we have available is zoo. Now, what is TS? TS is abbreviated as time series. Zoo is abbreviated as Z's ordered observation. Okay. So TS is used when you have regularly spaced, consistent information. Zoo, on the other hand, is used when you have irregular time series with arbitrary date, time, or indices. Okay, so here you can see you have an example of where TS is used and where Zoo is used. So you also have another point which says use TS for regular data and Zoo for irregular date indexed data. So if your data is irregular, then you would go with Zoo. If your data is regularly spaced and pretty easy to understand, then you will go with TS, which is time series. So here you have TS is used when the intervals are regular, when the data is very simple and efficient. Zoo is used when there are irregular dates. At the same time, it also has flexible indexing. And then you have XTS, which is extensible time series. Okay, this is used wherever you have financial information. And what is the specialty? It has very fast subsetting. Okay, so you can see an example in this part of the page. All right, and I think now once you see this, you would have a decent understanding of when, which library or which function to use. Also remember XTS, which is extensible time series, is used for financial or high frequency data. Do not forget this. Now, how do we plot time series in R? There are basically two ways to plot time series in R. The first one being plot function. The second one being autoplot. Autoplot is a part of ggplot2 library. Okay. And within ggplot2, when you use it, you can directly say library of ggplot, library of forecast, and autoplay or autoplot my underscore ts. Now, what is my underscore ts? If anyone can write about it in the chat section, I think I would be very happy. However, my underscore ts happens to be the name of the data within which I'm trying to auto plot the graph for. Okay. So what is the workflow? You would be having local time series objects. You would call or you would use plot or auto plot. Then you would inspect the terms, trends, platforms, seasonality, etc. Then we have decomposing time series in R. Now, what do we mean by decomposing? As you can see, it is a very simple way of separating trend, seasonality, and residual. Okay. Now, what is a trend? What is a seasonality? And what is a residual is something we have already seen. Now, we'll talk a bit about decomposition in itself. So there are two types of decomposition. The first one is classical decomposition, as you can see. The second one is STL, that is seasonal trend decomposition. So in classical decomposition, you would split the series into trend, seasonal, and random components using moving average approach. But when we talk about STL, that is seasonal trend decomposition, it uses loss function. Okay, as you can see here, I have the spelling, and it is more robust and flexible, and it handles, the changing seasonality well. However, please do not compare with either, do not compare basic decomposition with STL variant of decomposition, because one is using loss function, the other one isn't. One is handling seasonality well, while in the other one, you are using it when you know that the series is with fixed seasonality. So A and B are two entirely different things and they are not the same. Now, when you're working on decomposition, you would have a few outputs. Firstly, you would have the original series. The second one is trend component. Third one is seasonal. And fourth one is residual. So in the original series, you would be reading the raw information, right? The information which is not at all clean. To calculate the trend component, you would be using smooth line. Now, what do you mean by smooth line? It's a line where there are not a lot of crest and trough. Okay. Then you know what's a seasonal component? It is kind of getting isolated, and repeating the pattern, right? And finally, you have residuals. Residuals are something like errors, and like whatever is remaining, or whatever is the variant of current data remaining. Residual is something that cannot be just removed just like that. Then you have stationarity. Great. Now, we all know what is stationarity, I think, as the name itself tells you. Okay, now why do we need it and what is it is the first step that we need to understand. Okay, so when you are working on time series, yeah, whenever we are working on time series, here the statistical properties do not change with time. For example, if today the value of mean or average is a plus b by 2, 10 years later also it will still be the same. It will be a plus b by 2. Okay. So what happens is, in stationarity, a time series is stationary if its statistical properties do not change over time. Okay. And in practice, it stays stable rather than drifting or repeating seasonal patterns. Okay. And this is the beauty of stationarity. So in stationarity, you would be having a constant mean, a constant variance, and probably no trend of being seasonal. Okay. So why does this matter? Like, how would stationarity make any difference to ARIMA model? Now, as I said, when we are working on ARIMA, we expect that the data is stationary before fitting it into relationships over others. Okay. Now, when this assumption is not satisfied, that is when you might have to either change or you might have to work on forecast to make it better, right? So forecast can become very unstable and very, very less accurate only because of the information not being available as and when needed. Okay. So you have stationary data which supports a few, and then you have unstationary or non-stationary data which might not give you a reliable output or a forecast, but can still be used very. I mean, it can be used the way we needed to solve a problem statement in time series. Then comes testing and achieving stationarity. Again, in order to do this, you have ADF, which is augmented Dickey-Fuller test. Okay. Please remember the name is Dickey. Do read it completely and do not read only the half name. Right. So you have augmented Dickey-Fuller test, and you also have differencing test. Now, both of them essentially do the same thing. They test and they achieve stationarity. However, in augmented Dickey-Fuller test, the value is assumed to be less than 0.05, which means that the series is stationary. Okay. Now, when we like what happens when you do ADF, it firstly removes any kind of understanding on the data, like probably removing things which are not needed, etc., and are things that can be done very easily here. And in order to work on augmented Dickey-Fuller test, here you can see you have ADF test. Okay. And here, as you can see, you have ADF test once again. Okay. So this is the workflow. As you can see, you would first be generating a plot. Then you would be, once the plot is done, you would be making an ADF, augmented Dickey-Fuller test. And then you would be differentiating the data if needed You would again go in for a test, and finally you will come out with ARIMA, regressive integrated moving average. Now, when you say you're fitting ARIMA goes and fits to the model. Okay, please remember that. Now, what are different stationary workflows? So the first one is to plot the series. The second one, as discussed, is to run ADF test. The third one is to apply differentiation, and the fourth one is to retest and refit your ARIMA model to confirm stationarity, and then you can go ahead and complete the complete modeling of your time series analysis. So let us understand ARIMA with formula this time rather than very simple theoretical understanding. So firstly, ARIMA is PDQ. Okay, P is AR, so AR, then differencing is also I, and then you have MA. So it wouldn't be wrong to say this is how ARIMA came into existence. Now, what happens when you are using PDQ, and what is the value of P? So when you're using P, there is a number of past value lags in the auto-compressive component. All these lags or all these values, they then go into the next phase, that is differencing order, and they get differenced a number of times before the series is differenced to achieve the stationarity. And then you have MA, moving average. So it is the number of past forecast errors in moving average component. So with this, we have successfully completed the first part of unit 5. Okay. So first part of unit 5 is complete. And if in case you have really enjoyed the session, then do not forget to get back to the second video on 5th unit, which would be dealing a bit more about ARIMA, GARIMA, or time series, etc. So in the coming up next, you have the second part, okay, of the unit 5, which is to be completed. Okay. And in the meanwhile, do you have any questions or anything that you feel is not hitting you or is not doing any good to you? You're free to drop a mail, or you're free to text me on the chat section below, so I can probably try to address your query and ensure it is resolved next. Thank you very much. You all have a good day. This is me, Varun, signing off. Thank you all.